I want to just kind of say a little bit about what we're sort of going to be focusing on. And pretty much in 341, picture that you see over and over again, and this is the picture that you've seen in 6003 and 6011, is talking about systems. And so the input to the system might be a discrete time signal. It might be a continuous time signal. The output would be written similarly. And then if it's an LTI system, then there's a system function, and depending on whether we're talking continuous time or discrete time, it may be h of s, it may be h of z. We may be talking about, in the frequency domain, if this is the continuous time frequency variable, in discrete time, we would typically write things that way. And then there's the notion, for example, of talking about the impulse response, and then the relationship between the output and the input and the impulse response. And so all of you presumably have seen equations of this type where I would write h of n convolved with x of n, or I would write y of t is h of t convolved with x of t. And then in talking about these systems, we would have various kinds of notions that would come up. For example, questions of causality, questions of stability. We would be talking about Z transforms. We would be talking about time invariance. We would be talking about linearity, Laplace transforms, et cetera. And that's sort of the typical signals and systems kind of notion and discussion. A lot of the systems that we'll be talking about are systems that are characterized by linear constant coefficient difference equations. And so what does a linear constant coefficient difference equation correspond to? Well, the kind of generic form of it is you've got a sum of coefficients multiplying delayed replicas of the output, and that's equal to a linear combination of delayed replicas of the input. And so this would be k equals 0 to n, and this would be k equals 0 to m. And so this is the kind of generic form of the linear constant coefficient difference equation. Linear meaning not necessarily that it's a linear system, but it's a linear combination. Constant coefficient obviously meaning that these coefficients are constant. And difference equation, well, there actually aren't differences in there, but historically it's called a difference equation because if you took a differential equation and then you replace the derivatives by differences, then you're going to get something of this form. And so historically that's kind of where the terminology comes from. Now, there are a lot of things about this equation that are often misconceptions. So, well, first of all, just in terms of terminology, I would typically, people in the field would typically refer to this equation as an nth order linear constant coefficient difference equation because of the number of terms involving the delays of the output. But then sometimes we end up with just all these AKs except for k equals 0 equal to 0. And then we would end up talking about it as an nth order equation. And you kind of wonder, or could ask, well, why don't you talk about it as an n comma nth order equation, where it's n on the left side, m on the right side? And the basic answer to that is because sort of the order of the equation, and probably most of you know this, and you'll see it when we talk about flow graph structures, that the number in the implementation, the number of delay registers that are needed is the greater of n or m. And most typically, n is greater than m. And so that's why it's called nth order. So you'll see that terminology. Now, other kinds of questions that you can ask that it's important to get sorted out about linear constant coefficient difference equations is this, if I give you the input x of n for the system, does this equation uniquely specify the output? And in my typical lecturing mode, I'd sort of put that question out to the class. I'd ask for hands. I'm trying to break that style of lecturing. But I'm still going to do it, I guess, just so I get this feedback. So how many of you would say that if I gave you the coefficients, the a's and the b's, and I gave you the input, that uniquely specifies the output? How many of you would say that? Well, the answer is it does not. And there are multiple reasons for that. So one reason is that there's the whole issue of initial conditions, or that kind of relates to the homogeneous solution. That is, you can always add a homogeneous solution to any solution and it'll still satisfy the equation. So this equation is a constraint between the input and the output. It's not a mapping from the input to the output. So then there are questions that come up of how do I make it unique? Well, maybe I specify something that pins down the homogeneous solution, and now there's a unique relationship between the input and the output. And then in that case, does that correspond to a linear system? Does it correspond to a time invariant system? And those are also kind of tricky questions. And the answer is, and is it causal? And a lot of the answer to that depends on how I specify this homogeneous solution. Furthermore, if now suppose I said, here's the difference equation, and I'm telling you that in addition to specifying the difference equation, I'm also telling you that the system is linear and time invariant. Can I now conclude that the system is causal? No. Can I conclude that with this information, knowing x of n, that y of n is uniquely specified? No. And these are all things that you want to get sorted out quickly. They're straightforward. The answers to those straightforward. How to think about it is straightforward. Now, something I can do is I can take that equation, and let's suppose that that A0 is equal to 1. It doesn't have to be, but I can divide it out. And then let me just rewrite that equation so that I'll write it as y of n is the sum from 1 to n. I guess I have a minus sign now because I'm going to take it over to the other side. A sub k, y of n minus k, plus the sum k equals 0 to m, b sub k, x of n minus k. Okay, now can I say that the system is causal? Because now the way I've written it, I'm generating y of n at any n by only using past values of y and current and past values of x. So then, is it causal? Well, clearly not, because if that equation wasn't, this equation is the same equation. I mean, I just took some terms over to the other side. So that's another thing to kind of get straightened out. So just because I wrote it in a form like this, which is called recursive, meaning I've written it where current values are generated from past values of the output and current and past values of the input, that means I'm running it in a certain way, recursively, but it doesn't mean that it's a causal system. You want to have that clearly straightened out in your mind. Now, one other thing is in terms, so this terminology which is recursive and non-recursive. And then some other terminology which we'll want to be referring to, which is FIR and IIR. So, for example, if I take this equation and I say that all of these AKs that I put over here are equal to 0, so I'm saying y of n is the sum of b sub k, x of n minus k. If I hit this with an impulse, then what I will generate for y of n is this sequence of these coefficients. This, in fact, is the convolution sum. So these b sub k's, in fact, would be the impulse response. And there's only a finite number of them. So the length of the impulse response is finite. On the other hand, if I wrote an equation that said y of n is equal to x of n plus a half y of n minus 1, and I run this equation, the impulse response, assuming this is LTI and causal, so that's the additional information I'm giving you, LTI and causal, this impulse response is going to go on forever. So this one is going to be IIR.